Today we're going to be talking about two different ideas. One is physical properties and physical changes. We're going to talk about how things appear and how they can change without actually going through any chemistry. And then the second thing we're going to talk about is the periodic table of elements, which is sort of the Bible of chemistry. It has a lot of information in it. We're going to start to just scratch the surface about how it's organized. First of all, let's take a look at physical properties. Here's how we can kind of define physical properties. First of all, a property is something that's an unchanging characteristic of a substance. Physical properties are unchanging behaviors and appearances of the substance by themselves, which is different from chemical properties. Here are some physical properties of substances. Color. We identify things in white light, let's say, in the same lighting conditions as having different colors. Copper, for example, looks that coppery reddish color, whereas silver looks a different color that we call silver, shiny and not as colored. Water doesn't appear to have any color. Iron often looks shiny and black. Iodine is a purple colored substance. Another one is odor. Some things have a characteristic smell, and we can identify that by that smell. Hardness. Hardness is, in other words, how easily does it dent? How easily can you hit it with something and make a mark? That's hardness. Malleability. Malleability comes from the same word part that the word mallet comes from, or hammer. So this is poundability. Can you take a hammer and pound it into something different? Different things have different malleabilities. Another one is ductility. This means how much can you stretch it? Is it stretchable? Some things stretch quite easily, some things don't. And another thing is its physical state, or sometimes this is called the phase of the material. And what we mean when we say phase is what phase usually is it at room temperature. For example, water is a pure substance. Its phase is normally liquid. Water can be solid and it can be gas, we know that, but when it's at room temperature under ordinary conditions, its state is a physical property. When we think about the physical states of substances, there's an explanation for that that has to do with atoms. Of course, we believe everything is made of atoms, and so how these atoms are organized must have something to do with what state they're in. For example, if a substance is a solid, it has a definite, in other words, a well-defined shape, and it has a definite volume. Here's why. The particles are packed together tightly in an orderly fashion. There are rows and columns. Somehow it's packed together in some way that makes the minimal amount of space, and that's why solids behave the way they do. Liquids have definite volume, but they don't have definite shape. The particles are packed tightly together, but they're randomly oriented, and they're free to move around. Like that. You can see the particles moving around, but they're still packed together. In gases, the substance doesn't have a definite volume, and it doesn't have a definite shape. The particles instead are far apart. They're randomly oriented, and they're free to move around, and are bound only by the confines of whatever their container is. Like this. As the particles are bouncing around, you can see them moving anywhere they want to go. Chemical properties, on the other hand, are not physical properties. They're properties. They're unchanging characteristics of a substance. But it has to do with how does the substance behave in the presence of other substances. How does steel behave when it's with oxygen? How does sodium behave when it's with chlorine? Those are chemical properties. Mostly right now we're going to focus on physical properties, but then we're going to very quickly get into chemical properties of materials and spend most of our semester on the chemical properties of materials. A physical change is a change that a substance undergoes and doesn't lose its properties. Another way of saying this is that after the change, it's still the same substance. Start out with aluminum, you end up with aluminum, like in this picture here. This is a progression of something called die forming that happens industrially. You start out with this blank, flat piece of aluminum, and after going through several steps of manufacture, you end up with this part that's been stretched out from the aluminum because it's ductile and it's malleable. Before you started this process, it was aluminum. After you started the process, it's still aluminum, and so that was a physical change. A phase change is an example of a physical change. It's a shift from one physical state to another. This always involves either the gain or loss of energy. There's an energy exchange that goes along with the matter change. Here are examples of the phase changes, the three phases being solid, liquid, and gas. When a solid becomes a gas, we call that sublimation. Dry ice does this all the time. Other substances can do it too, but that's the most common example. The reverse process is called condensation, or another word for it is deposition, when a gas becomes a solid. So that's the reverse process of sublimation. When a liquid becomes a gas, we call that process vaporization. That's liquid becomes gas. And the reverse process we call condensation. From solid to liquid, we call that melting. That's a very common word. Everybody knows that. Sometimes it's called fusion. When liquid becomes a solid, we call that process freezing. So that's liquid becomes solid. So those are phase changes. They involve energy, as you know. Phase changes are physical changes, even though it sort of violates our definition. We said that a physical change is a change where the substance retains its properties. And we're watching this ice melt here, and certainly the properties are not being retained. Solid is a state. That's a property. And liquid is a state. That's a different property. And it has definitely changed states. However, phase changes are physical changes because of this. Before we started, we had water, H2O. After we finished, we had water, H2O. Solid water, liquid water, still water when we're done. And so that's a physical change. It's actually how the substance, or when the substance undergoes these physical changes, that's a physical property of the substance. And we have two ways of describing that are very common. One is called the melting point. The melting point of a substance is a way to identify it. It's a physical property of the substance, and it is the specific temperature at which a pure substance melts, or it freezes at the same temperature. And the boiling point is like that. It's the specific temperature at which a pure substance boils, or condenses. Boiling point for water, for example, is 100 degrees C. Always. That's a characteristic of water. It's a physical characteristic. And its freezing point is 0 degrees C. Always, when it's pure water. In a chemical change, you don't have the same thing after the change is done. It results in an entirely different substance, or it could be more than one substance, that has different properties. That's chemical change. Here's an example of chemical change. Hydrogen, like was in the Hindenburg balloon that you might have read about in the history class, combines with oxygen and makes water. Well, hydrogen is highly flammable, very flammable. Oxygen makes things burn hotter. It's an oxidizer. When you put them together, you get water, and water, you can put fires out with water. So something very flammable goes together with something that makes things burn hotter. When you're done, you don't have either of those characteristics. Instead, you have something that puts fire out. Another very similar example. There's a bucket full of charcoal roasting these fish. Charcoal is a fuel. It burns. Oxygen makes things burn hotter. Add oxygen to charcoal, and you produce carbon dioxide if it's a chemical change. Carbon dioxide, again, just like water, puts fires out. So the characteristics of both the fuel and the oxidizer are lost. Something completely different has been formed. We're going to look at the organization of the periodic table here. The periodic table can roughly be divided into two main categories, and there's a dividing line. Think about a line that runs underneath boron, silicon, arsenic, tellurium, and astatine. That's a boundary on the periodic table. Things to the right of this boundary are called nonmetals, and things to the left of that boundary are called metals. That's the main division of the periodic table. And then you can see they're color-coded here. The nonmetals are yellow and the metals are blue. And there's an exception. Hydrogen over here, it's on the left-hand side, but it's really a nonmetal. And then there are some green things that aren't really blue or yellow, and we're going to talk about those in a little bit. But that's the main division in the periodic table. That distinction between metal and nonmetal is going to be very important. Let's explore the properties of metals first of all. Here's what metals are like. They're very ductile. You can stretch them. And so we have an example of a bunch of different parts here. All of these started out as flat blank sheets of metal. And by the process of die forming, they've been stretched out into longer, thinner objects. And over here we see a guy pounding on a piece of metal, and that mallet that he's using indicates that it's malleable. Metals will shape. They'll form into other substances very readily. It's a property of metals. Another property of metals is that they're lustrous, or in other words, they're shiny. It's another word for it. And we can see this metal glassed window. It's reflective, and it keeps heat out of the building. Another property of metals is that they're good electrical conductors. And so we have copper wires in our houses and cars and electronic devices that pass electricity from one place to another because they're very good at conducting electricity. Metals are good for that. It's a property of metals. Another characteristic of metals is that they're good heat conductors. And we can see that in this picture here. We use iron frying pans and pots and stuff like that to get the energy from heat into whatever's inside the pot. We wouldn't make that out of something that wasn't a good heat conductor, so we always choose metals for that. The properties of nonmetals are almost exactly the opposite. Instead of being malleable and ductile, stretchable and bendable like metals are, nonmetals tend to be brittle. They're hard, and if you try and bend them or stretch them, they're just going to break. And a good example of that is pencil lead, which is carbon. It's not really lead. If you take a piece of pencil lead and try and bend that piece of pencil lead, it doesn't bend like a piece of aluminum wire would or a copper wire. It just breaks. It just snaps. It's brittleness. In contrast to being shiny, we see that nonmetals are dull. Like here's some sulfur in a tray here. It's this kind of a dull yellow-colored substance. It doesn't reflect light very well. The opposite of metals. Nonmetals are poor electrical conductors. They're bad at it. And so while the copper here conducts electricity, we coat the copper with a non-metal-based substance, a plastic usually, or some kind of a cloth in the old days, that's an insulator. It doesn't conduct electricity, so we keep the electricity from going out. It's not allowed to pass out of the wire because it's coated with something that doesn't conduct electricity. And nonmetals are also very bad at conducting heat. And so here's an example of where that's been used. This house has got a lot of windows in it, and that would normally let a lot of energy out in the winter or in the summer. But these windows are filled with argon, and argon is a non-metal gas, and that argon helps prevent heat from going into the house in the summer or out of the house in the winter. Now in between the metals and the non-metals we have these green things, the metalloids. The metalloids have the properties of metals sometimes. Sometimes they behave like metals. Sometimes they behave like non-metals, and it depends mostly on the conditions that surround them. A really important metalloid is this one right here, silicon, Si. Silicon is extremely important in our modern economy because silicon is used to make computer chips. What people discovered was you can change its ability to conduct electricity very easily by just altering the conditions around the silicon. And so we have very tiny submicroscopic switches that are made from just a few atoms of silicon, and that's what computer chips basically are. Millions of little tiny switching devices. Looking at the periodic table, another way that we can divide it is we can think about two zones. The first two columns and the last 6 columns are called the representative elements. These are fairly easy to study. They're fairly easy to make predictions about what they're going to do, how they're going to behave. In the middle we have the transition metals, or the transition elements, and that includes something called the inner transition elements, which are the ones that are down below on most periodic tables. The representative elements, we can make some easy rules for those, and they also have some very common characteristic features in groups. We're going to study those a lot at first, and then we'll start to drift into the transition metals later on. We're going to take a look at 5 of these groups of representative elements very closely because they have some features chemically that are very similar. They have similar chemical characteristics being in the same column. The first one we're going to focus in on are the alkali metals. Here are some characteristics of alkali metals. One, they're very reactive with water. You put alkali metals in water and you get a reaction. Here's what the reaction is. Water, which is H2O, everybody knows, will react with this metal, whatever it is, Am I'm going to say for alkali metal, and you're always going to get a thing called an alkali. That's why they're named alkali metals. The modern name for alkali is a base. It's sort of the opposite of an acid. And you're going to get hydrogen gas. And you also get a lot of heat. And hydrogen is a fuel. It burns in air, so the heat often ignites the hydrogen in the air that's around it, and then you get a fire. So this is a very reactive stuff. It's also, they're very soft. Alkali metals are soft. You can cut them with a jackknife most of the time, even though they're a metal. And another characteristic is they react with the halogens, the 7th column over here that we're going to look at later, and they make salts. So alkali metal plus halogen makes a salt. And when a chemist says salt, they don't always mean table salt. They mean a characteristic compound that's made from a metal plus a non-metal. Next group that we're going to look at is the alkaline earth metals. Alkaline earth metals are the 2nd column over, right next to the alkali metals. The alkaline earth metals have some substances in there that are common. Magnesium and calcium you've probably heard of before. Some of the others maybe not. They're fairly reactive with water. They're not like alkali metals where they violently react with water, but they're fairly reactive with water. They also react readily with oxygen and with nonmetals, particularly the halogens. Another characteristic group that we're going to look at is the chalcogens. The chalcogens right here, this is oxygen's column. Oxygen, sulfur, selenium are the most famous of these. These things tend to form compounds pretty easily. They're fairly reactive. Oxygen reacts with all kinds of stuff. In fact, we have to protect ourselves from oxygen, which seems weird because we need it to live, but oxygen will modify our tissues and oxidize them. So we have to take things like vitamin C that are antioxidants to protect us from chalcogens. The next column that we're going to look at is the halogens. Halogen, the word really literally means salt former. And these halogens react with all kinds of metals to make different kinds of salts. These things are either gases or near gases at room temperature. They all end in "ene." They're famous: fluorine, chlorine, bromine. Iodine is a solid, but it's really close to being a liquid. And astatine is extremely rare. So those are the halogens. They have a characteristic odor. They smell like bleach. And all of them smell like bleach, and the reason is because chlorine, which is a halogen, is in bleach. The last column we're going to look at is called the noble gases, and these things have the chemical characteristic of not being chemically reactive. They don't react with anything, no matter what you put with it, without some help. They're very standoffish. That's where their name comes from, noble gases. And they are familiar. The names we've heard before: helium, neon, argon is in light bulbs, krypton, xenon, and radon. These are the noble gases. These things are very well known to not react with stuff. Another name for the noble gases is the inert gases. React with almost nothing.